Hey guys, welcome back. This is Mr. Kim, and I'm going to go over the 2025 AP Chemistry FRQ question number three. Number three, white phosphorus is composed of P4 molecules with a tetrahedral structure as shown in the diagram on the left or below in this case. Each P atom is bonded to other three P atoms by single bonds as shown in the incomplete Lewis diagram on the right. Now, part A, in the box in part A, complete the Lewis diagram for the P4 by drawing the non-bonding electrons. Well, this one's quite easy to do because what do we know? In order to do Lewis diagram, we need to see the total number of valence electrons, right? Because remember, it's Vesper or Viseper, right? Theory. So we've got to get the total valence electrons. Phosphorus has a total number of 5 valence electrons. Therefore, having 4 phosphorus and white phosphorus, we have a total of 20 valence electrons that needs to be represented by our Lewis diagram. The diagram already has 1, 2, 3, 4, 5, 6 bonds, and at 2 electrons per bond, that's 12 valence electrons that have been used up, which means that we need to take into consideration 8 valence electrons. So how do you show 8 valence electrons? Well, we know that each of the phosphorus is going to show an octet. So therefore, if we take 8 divided by 4, that's 2 valence electrons. Oh, per atom, and therefore the easiest thing to do is to put 2 valence electrons on each of the phosphorus, and then you'll get a total of 20 valence electrons, and that is the answer for part A. Let's move on. Part B, the reaction of white phosphorus with oxygen to form P4O10 is thermodynamically favorable at 298 kelvins. The reaction is represented by equation number one. Let's see, the entropy change of the reaction is negative using particle level reasoning. Explain why the entropy decreases as the reaction progresses. All right, so I'm going to try to answer this as a student would answer it, right? BI. All right, so what do we know about this thing? We know that we start with one molecule of one mole or one molecule of solid, and then we have 5 moles or 5 molecules of our gas, which in total becomes only 1 mole of solid, right? So I think the key here is the disappearance of the gas in our products as it goes to products. So what we could say is as reactants, right? The reaction is comprised of, right, 1 mole of solid reacting with 5 moles of gaseous dioxygen. As reaction goes to completion, we have only 1 mole of solid P4O10. So what does that tell you? This tells you that there's less number of gaseous molecules on the product side, right? So therefore, having less numbers of gas molecules on the product side will result in lowering of the entropy. Okay. All right, so that takes care of BI. Let's move on. Part two, the enthalpy change of the reaction, delta H, is also negative. A student claims that the favorability of the reaction is driven by enthalpy and not entropy. Is the student's claim correct? Justify your answer by using the relationship between delta G, delta H, and delta S. Well, what do we know about this? Before we get started, right? So let me put it down here. I2, we know that the equation is delta G equals delta H minus T delta S. And I'm sure in your in our AP chemistry textbook, in our case, we zoomed all. We know that the four conditions that we have to ensure spontaneity, right? Spontaneity happens when delta G is negative, right? Or AKA favorable conditions. And how do you get that? You get that when our reaction or delta H has a negative value in case exothermic, right? And then because of the expression that negative T delta S, we know that if you have a positive value for entropy, then it will end up with a negative value, which will eventually end up with negative delta G in all conditions, right? So this is a condition that gives rise to uh, a favorable or spontaneous condition. And conversely, the opposite is true, right? This is what never, right? Favorable or spontaneous. So let's look at what's going on in our system. In our system, we have delta H is negative and delta S is also negative, right? What do we know about this situation? In this situation, delta S is not going to help with the system because um, our temperature in Kelvin is always going to be positive value. So that positive Kelvin, which is actually here somewhere, right? I think it's here. Well, you know the temperature in Kelvin is never going to be negative value, right? It's going to be absolute zero or a positive value. So in this case, a positive delta T, times a negative entropy is going to give you a negative value, but then you're subtracting that, which is going to be a positive outcome for delta G evaluation. So therefore, we know that this negative delta S is not helping, okay? Whereas our enthalpy value being negative helps our delta G be all it could be, which is negative, right? So in this case, what happened? The student says that it's the favorability is driven by enthalpy and not entropy. And in this case, we would say we agree. So what do we say? Always start your answer with whether you agree or not agree, right? So claim correct. So use the words that the problem, what happened? Use the words that the problem gives you, right? So I would say the student is correct, right? You start off with that. And then what do we say? We say that, uh, and it says justified by relationship between. So I say a favorable condition um, arises when you have negative delta G or gives free energy, right? The equation for delta G equals delta H minus T delta S. A negative delta H will support the delta G to be a negative value. However, the positive delta S means, oh, okay, I'm sorry. I said it's negative, right? However, the not positive, the negative, right? So, oops. So the negative, right? Delta S means that the expression negative T delta S would be positive, and therefore um, it will not help delta G be negative. In other words, a favorable condition. Okay, so that should take care of our B2. Let's move on with our answers. Um, okay, so what does this one say? P410 reacts exothermically with water to form phosphoric acid as represented by equation 2. A chemist uses a calorimetry experiment to determine the enthalpy change for the reaction as represented by the following diagram. So we have a calorimeter, and let's see what the question is asking us to do. So going to our problem, it says the chemist carries out a calorimetry experiment and records the following information, and we have the values right here. Calculate the amount of heat that is released during the experiment. Assume that the specific heat of the solution is the same as that of water. All right, so we have some values right here, right? So we have initial temperature and final temperature. Oh, sorry, I don't keep moving. Initial temperature, final temperature, that gives us a delta T value of, what is that? That's 22.38 minus 22. So that gives me 0.38 degrees Celsius for our delta T. All right, what else we got? We got our mass of our white phosphorus, and we have a molar mass, we have mass of the water, and with specific heat. All right, so what are we looking at? We're looking at the amount of heat released during the experiment, which means that it's the heat that was released by the white phosphorus, right? Um, so let's see. That is true. However, the temperature change just keeps moving. Temperature change is that of this is of complete mass, right? That's the mass of water plus the white phosphorus. Or the mass of water and then white phosphorus just a small amount, but it is there. So let's go and set up our problems. Like how I tell all my students, right? When you write here, you want to write 3CI. I don't know if that's the word 3CI parentheses. And then what they're asking you is what? Calculate the amount of heat. So I'm going to put Q is equal to and leave it at that. And let's do our work. So to do our work, I'm going to write some information down. Our delta T as calculated is 0.38 degrees Celsius. We are given our mass, right? And we said it's a total mass, right? So it's going to be the summation of that. So mass total is equal to 100.1 grams. Remember sig figs. So it's going to be 100.1 grams because it's the smallest of decimals for addition. Okay, so we got our specific heat is going to be 4.18 joules per gram degree Celsius. And then we have our Q value, which is our unknown. So let's go ahead and solve this, right? So we know that Q equals MC delta T is the equation we're going to use. And we got our mass is 100.1 grams. We got C 4.18 joules per gram degree Celsius. And we got our delta T value, which is 0.38 degrees Celsius. We know these values cancel out, and that should give us a value of, let's see, 159 joules. However, be careful, right? I always tell my students that you have to circle, right? Important portions, as kilojoules, right? So we got to do your kilojoules conversion, which is going to be what? It's going to be 1 kilojoules per thousand, right? It's going to be, now let's look at our sig figs. Sig figs are going to be limited to 3 sig figures. So it is going to be equal to 0.16 kilojoules. So I'm going to go up here and put 0.16 kilojoules, circle it. It's a good practice, and we are done with 3CI. Let's go to part 2. Calculate the value of delta H for the equation. Include the signs in your answer. All right, so let's get solved on this one. So how do we do this one? We want the delta H for the reaction, right? And what do we know? I guess if I can go back and show you the equation that we have is right here, right? If you look at the equation, what do we know? It's a 1 mole of P4O10 per 1 mole of reaction. Okay? So what does that mean? Let's go back to this question. So what do we got? We got our Q value, right? And by the way, the Q value is heat is released. So one thing I forgot to mention is that has to be actually a negative value, right? Because it's released, right? Be careful with that. All right, so we have that. I'm going to bring that value across, which means that it's negative 0.16 kilojoules. Okay. All right, so what do we got? We got this, and we know that we need the moles of, well, we know that this was produced by all of the white phosphorus that had reacted, right? So that's per, right? All total number of P4O10, right? So we can figure out per mole. So let's go ahead and do that. So in order to do that, what do we need? First of all, it says to calculate. So I'm going to say, which is 3C double I. It says calculate the value. So I'm gonna write this down. And again, I say this to my students because I say this helps you keep track of what you're supposed to do. Include signs in your answer and so forth. Okay, here we go. So let's go ahead and solve this. So we know that we need the number of moles of our P4O10, right? So we have, let's do a dimensional analysis. We got 0.100 grams of P4O10, right? And we are given the molar mass, right? 283.9 grams per 1 mole of P4O10, right? So that gives us mole of P4O10, and I don't know if I calculated that value, and I think I did, right? It should be 3.52 times 10 to the minus 4 moles of P4O10. All right, so what does that mean? Well, that's the total number of moles of P4O10 that reacted, which ended up resulting in the total amount of heat that was released, which is 0.616 kilojoules, right? So let's go ahead and continue our investigation. It's going to be negative 0.16 kilojoules, and that was released by all of the 3.52 times 10 to the minus 4 moles of our P4O10. All right. But we're not done here because what do we know? We know that we want it per reaction, right? And remember, the stoichiometry is it was 1 mole of P4O10 to 1 mole of the reaction. And this should give us the proper unit that we need. All right, so what does that get us? That gets us negative, it should be 2 sig figs, I believe. Let's go with it. So negative 450 kilojoules per mole of the reaction. So I'm just go over here. It doesn't take too much time, right? Like that, and circle it for the readers. Okay, so that takes care of part C, and we're feeling good because why? We're chugging along. All right, so let's look at D. The chemist weighed out 0.1 grams of P4O10 and 100 grams of water to perform a second trial. In the second trial, some of the solid white phosphorus stuck to the weighing paper and was not transferred to the calorimeter. Given that the P4O10 is the limiting reactant, would the delta T for the second trial be greater than, less than, or equal to the value of the first trial? Let's think about this for a second before we start answering this. So we know that essentially because there's going to be some white phosphorus stuck on the paper, it's not entering the calorimeter or the reaction chamber, right? Which means the total number of moles of calorimeter of the white phosphorus is also going to be less, right? So if the total number of the moles less, think of it this way. It's like that's the fuel that is used to drive the raising of the temperature or the delta T. So since we have less white phosphorus or less quote unquote fuel, we would expect the water to not go up as much, right? Because imagine you're like heating the water by burning white phosphorus. So we know that the delta T is going to be less, right? So we're going to start our answer just like that. So for 3D, we're going to say the delta T of the second trial will be less than that of the first trial, right? Now, it says justify your answer. So let's go ahead and justify, right? So we would say that you can do it in terms of mathematics too, right? So what do we know? We know that Q equals MC delta T, right? Which means that delta T, right, is dictated by MC, right? I'm sorry, not MC, Q over MC, right? By Q divided by MC. Okay. So the P4, my pen is having a hard time. My apologies. The P4O10 being stuck on paper means less number of moles of our white phosphorus, O10, entering the calorimeter. Less number of P4O10 means the total heat released will also be less, right? That's Q, or negative Q in this case, right? However, what do we know? P4O10 is really what? 0.1 gram, right? P4O10 right, at 0.100 grams, right, is not a significant amount of the total mass, which is what? Water plus P4O10, right? Therefore, in the expression, delta T is equal to Q over MC. The Q will be smaller value, excuse my handwriting, but the MC will not deviate much from trial one's values. Okay, I hope that makes sense to you guys. All right, so that's part D. Let's go on to part E. This is a long one, right? Let's see. P4 solid also reacts readily with dichlorine to produce phosphorus trichloride, PCl3. When it reacts with the dichloride, dichlorine in an equilibrium process to produce phosphorus pentachloride. The reactions are represented by the equations 3 and 4. So let's take a look. Calculate the standard enthalpy of the formation of PCl5 represented by equation 5. Well, this is just your straight up forward Hess's law, isn't it? So let's take a look. So we got our PCl5 on the correct side over here, right? What do we know? We also know that the P4 seems to be in the correct side. So we know that there's no flipping involved, which means that the signs of our both our two enthalpy values are going to stay the same, hopefully, right? All right, so what do we know? Chlorine is in the same side, right? So we got 6 dichlorine here and 1 dichlorine on the bottom. And then what do we got? We got PCl3 on either side. We know that there's no phosphorus trichloride present in the equation 5 or the overall reaction. So we know we got to cancel these guys out. So how do we cancel these guys out? Well, we could multiply the bottom, right, by 4. Sorry about that. If we can multiply the bottom by 4, but if we do multiply the bottom by the 4, and then what happens, the coefficients don't work out. You can do this, and then what happens is you have to simplify. The pun intended, the more simpler thing to do here would actually be to multiply the top by quarter, isn't it, right? Because if we did that, then our PCl3 would be 1 in both equation 3 and equation 4. So we are going to go and do that. And what we're going to do is we're going to take this entire thing all the way out to our enthalpy value and multiply by 4, a quarter. Okay, so let's go and do that. And let's say it says calculate standard enthalpy formation, so they want that. So I'm going to put, what is this? This is question number 3, part E, right? And it asks to calculate, right, heat of formation. So I'm going to leave that, come back and write the values, but let's get started, right? So it's going to be what? P4 plus 6 dichlorine goes to 4 PCl3, and our enthalpy value is negative 1148. And we're going to multiply this, remember, by a quarter, which gives you 1/4 P4 plus 1/4 chlorine. Oh, no, I'm sorry, it's 6 over here, so it's 6 over 4, right? Gives you, it's going to be 1 PCl3, like that. And then what's that going to be? That value is going to be divided by 4, and what is that? That's going to be negative 287. Okay. All right, what else we know? Well, 6 over 4, what is that, guys, right? 6 over 4 is actually 3 over 2, isn't it? Right? So I'm going to write 3 over 2 over here, right? Let's continue. And then what we have on the bottom is we're just going to go ahead and bring down our PCl3 plus Cl2 goes to PCl5, right? And we know that with these two equations, that cancels out. And this is 1, which is 2 over 2, right? So now what do we get? If we sum the two and bringing this straight down is negative 88, right? We get 1/4 P4 plus 3 over 2 plus 2 over 2 is 5 over 2 dichlorine, giving you our PCl5, right? And what do you know? That's the same as the equation that's in equation 5. So what does that mean? That means that it's literally just going to be negative 287 minus 88, which is negative 375. And what's the unit? That's going to be kilojoules per mole of reaction, right? So right up here, I'm going to write negative 375 kilojoules per mole of our reaction. Circle it for the readers, and we are done with 3E. All right, moving on. We got F. The following particle level diagram represents the contents of the vessel in an equilibrium mixture at 546 Kelvin involving equation 4. So just a mental note, there is a temperature there. I don't know if we need it, just in case we need it later. Equation 4 for the reaction that occurs is shown below. Equation 4 is yada, yada, yada. And what else? What is this asking? If each particle in the diagram represents a partial pressure of 1.00 ATM, what is the value of Kp for the equilibrium mixture at 546 kelvins? All right, so we are going to have to answer this. It's going to be 3Fi, and they want to know what Kp is, so I'm going to do that. And let's just start getting some values out, right? So we know that we could write the expression for our Kp, right? What is our expression for our Kp? Our Kp is equal to, it's always our products or reactants, right, kids, right? So it's going to be pressure of our PCl5 all over the partial pressure of PCl3 times the partial pressure of our chloride, okay? We don't have these values. That's what we're supposed to look for. But they said it's 1 ATM per particle, right? So let's go back and gather that data, okay? So we need that from our particle diagram. And it's 1.00 ATM per particle, right? So what do we got? We got for chlorine, we got 1, 2, 3, 4, 5, 6. So we got 6 particles. And then for our PCl3, we got, let's see, 1, 2, I count 2 particles. And then for our PCl5, we got, I count 1, 2, 3, 4, 4 particles, right? Am I right? What do you think? Yes. All right, so remember this. So we know that you don't have to do this, right? But essentially, what is it? You're going to have to, this is the logic, right? Like that, to say that your dichlorine is 6.00 ATM. And using the same logic and same math, you will realize that this is 2.00 and this is 4.00 ATM. Okay? All right, so what does that mean? That means let's now go back and we can fill in these things, right? So we know that PCl5, my mind is that of a snail. That's going to be what, 4? Right? 4. So that's going to be 4.00 ATM. Am I going to write? Okay. Divided by our PCl3, I believe, was 6.00 ATM times 2.00 ATM. Not to make you guys feel bad if you didn't do as well here, but this is actually quite e fortuitous because and easy because it's a 1-to-1-to-1 ratio, so we don't have to deal with exponents or anything like that, right? So then plugging these values, you get 4 over 12 and 4 over 12, right? Gives you 0 point what? Uh, 3, 0. No, not 0.300. It's a 0.333, right? 0.333. And that is our value, right? And we're done with the first part. All right, let's go to part 2. The last part, equation 4 for the reaction that occurs is shown, blah, blah, blah. Does the value of Kp increase, decrease, or remain the same when the temperature is increased to 596 kelvins? Justify your answer based on our delta H2, right? All right, so what do we got? We got, I'm going back, right, for this thing, and then we said, where is our delta H? All right, is it this? Right. So we know that the value here is what do we know? It's a negative symbol, right? So it's exothermic, right? So let's gather our data here. Our information is right? Couple of things. One, we're gonna let's just get started. I want to put some area where I'm gonna this is problem number 3, FI2, right? I know that I want to leave some space for me to write the answer, but let's gather some data, right? So we know that delta H2 is negative, right? Or exothermic. What else? Go back and gather some data here. We know that Kp was equilibrium mixture at 546, right? So what is our Kp? Kp, all right, so we got this. And then sorry, and then we also know that Kp was equal to 0.333 at 546 kelvins, right? So what does that mean? That means this reaction is exothermic. Product is heat is on the product side. So therefore, what happens if the temperature goes up? That means there's excess heat, which means that we have more products, and therefore the equilibrium will shift towards the reactant side, right? So what are some of the things that we need to mention here to get on the good graces of our readers? Is you probably want to talk about Le Chatelier, right? You want to probably mention that. So we know that the value will decrease. So we'll start with that, right? So we'll say that the Kp will decrease. Um, and how do we answer this, right? The reaction, right, is, oh, I just noticed the delta H2 is right here, right? Right here. It's been covered by my little bar for the Zoom. That's why I didn't see it. But it doesn't matter. It's the same conclusion, or negative, right? Is an exothermic reaction, which means what? That heat, right, is a product, right? Um, so raising the temperature, right? Temperature will add heat to the product side. Um, Le Chatelier's principle, right, dictates that in this situation, the reaction will be driven backwards. What does that mean? That means, right? That means the number of products, I'm just waiting for my computer to catch up. That means the uh, P for PCl5 will get smaller, and both the partial pressures of PCl3 and partial pressure of Cl2 will become larger values. Making a new Kp that is what? That will be smaller, right? That will be smaller. There it is. All right, so that's it. This is the answers to question 3. It wasn't as bad, I think, right? So I hope you got all of this correct, and I hope this was helpful. Thank you for watching, and I'll see you in the next video.